Another interesting mathematical application of all of this is thinking about how many digits we have here. And so since this is base 2, or binary, it's base 2, and since we have 3 digits, I'm going to raise it to the third power, and this tells us how many different possible combinations there are, which is going to be 8. If I added on another digit, so that would be 4-bit binary, 2 to the 4th is going to be 16 different possible combinations. And if I was to add on a 5th, there would be 32. So we see that these are all powers of 2. Now, this is not uncommon. If we had 3 digits of decimal that you're familiar with, we could go from 0 to 999. How many different possible combinations of 0 through 9s are there with 3 digits? Well, there happen to be 1,000 because we have to include 0. Well, that's kind of interesting because that's base 10 to the third power. Because there are 3 digits, there are going to be 1,000 different values, and this works for any number combination. As it turns out, math works in any number system just the same way. We just have to condition ourselves to know that this one has a terminal character of 1, this one has a terminal character of 9. There are other things that we can realize about this that's actually pretty fun as well. If we look at the first column, there's a pattern. It goes 0, 1, 0, 1, 0, 1, 0, 1, and that'll go on forever and ever and ever and ever. If you go back and watch the binary counter run and only look at the first LED, it just sits there and blinks on and off. But wait a second, this one does the same thing. It's just for twice as long. This one goes 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1 forever and ever and ever. This one goes 0, 0, 0, 0, so that's 4 zeros, 4 ones, 4 zeros, 4 ones, and here's the challenge. How many zeros and how many ones in the next column with 4 bits? Oh, 8 zeros followed by 8 ones. What's the next one? 16 zeros followed by 16 ones. And this is the same way as counting here. If we look at this first column, and by the way, it keeps on going, 16, 32, 64, 128, 256, 512, 24, 10, 24, 20, 48, 40, 96. These are all powers of 2. It goes back to this idea of powers of 2. The same thing happens over here, 0 through 9. If you were to write out 0 through 999, the first column would have a pattern. It'd be 0 through 9, 0 through 9, 0 through 9. The second column would be 10 zeros, 10 ones, 10 twos, and it'd repeat out to 9s, and then it'd start over at zeros. And so those patterns keep on going. So this is kind of important to understand just our basic number systems. Another question that people might have is, why do we even use decimal? Well, I've been told that the ancient Babylonians used base 60, meaning they had 60 different characters for 0 through 59. And that's where we get 60 minutes in a day and 360 degrees in a circle. And that's what they were based on. But we, in our brains, we start forgetting digits. And really, the reason why we've settled as a society on base 10 is, well, we have 10 digits on our fingers. And at least that's the basic understanding that everybody has. And this is why Roman numerals were kind of wiped away from this. We can remember 10 individual numbers. And once you get up beyond maybe 20 different numbers, it'd be a little bit difficult to do math, at least for our brains. For a computer, it doesn't care. It can do math in any kind of combination. And that's why we use math in the way that we do, is computing, is because it helps us to do much more complicated things. But the most interesting part about this is this math that we do here is what works in your cell phone, in your computer, in your car, in your microwave. It is using these different combinations of zeros and ones to be able to create mathematical outcomes that are predictable. And this has been around for a long time. A lot of this is called Boolean logic or digital logic.